Thanks. Sorry for being a bit late here. For people who are from Berkeley, we know that Berkeley lecture always starts 10 minutes after the hour. So we're right on time now. Thank you very much for inviting me here. It's great to be able to teach to this class, the first year, I guess. So, okay, so today is 4.5. How many hours do I have today?
You have 3 times 1.5 hours.
3 times 1.5 hours. Very good. So I'm going to talk about the theme of today's lectures will be on information theory of wireless networks. So let me just say a few words of what I mean by that, and then we'll go from there. So one of the holy grail of information theory is essentially to extend Shannon's theory for point-to-point communication to networks. So point-to-point communication, Shannon theory has already a huge amount of impact. Almost any modern-day communication system you can think of is basically designed on the basis of information theory. If you look at 1948 paper, its focus is purely on a point-to-point context from one sender to one receiver. So we've been working pretty hard on this problem, which is to extend the theory to networks when you have multiple nodes communicating to each other. So today I want to propose some recent results that we have and others have to try to make progress to extend the theory to wireless networks. So let's see where we are. So the focus is on wireless networks. So let me talk a few words about the wireless medium. So there are 3 important aspects of the wireless medium that I want to worry about. One is the broadcast. When you send a signal, multiple receivers simultaneously receive that signal. Number 2 is interference. Signals go over the air, and therefore multiple received signals superimpose at a receiver and create interference. Number 3 is the fact that in a wireless network, there's a very high dynamic range in the channel strength between different nodes. So we want a model which can model all 3 phenomena: broadcast, superposition of signals, and the fact that channel strength can be very different. The standard model that a lot of people in this field has been using is, of course, the additive model, the additive Gaussian model, where the received signal at a particular node J is the superposition of the signals transmitted at node I through a gain Gij plus noise. So this is the basic model, and of course there's a lot of more fancy version of this model, such as fading and frequency selective fading, flat fading, and so forth. But let's just look at this very basic model here. And this is sort of the workhorse of much of wireless information theory, so to speak. So, so essentially this is now a Gaussian network. So let us quickly review what we know about Gaussian network and what we don't know. So what we know is, of course, first, Shannon's result on the point-to-point capacity. As we all know, the famous formula, the capacity is log of 1 plus signal-noise ratio. So this is a test of the prerequisite of this class. So I hope this is not a surprise to anyone. Good, all right. Would it surprise you? Okay, good. All right. Capacity is log of 1 plus the signal-to-noise ratio is the famous Shannon's formula. So ever since Shannon came up with formulas of this type, everybody, of course, wants to have the same type of results for networks. Very simple formula, very explicit, depends on channel parameter, the signal-noise ratio in this case. Success came very early. So in the early 1970s, simultaneously, Al-Shwedi and Liao came up with the generalization of this basic result to the multiple access case. Actually, they not only solved the Gaussian case, but they also solved the general case. Or more precisely, they solved the general case and later specialized to the Gaussian case by others. But their result are the main results. Here we have 2 senders simultaneously sending information to a common receiver. Here, the notion of capacity is extended to the notion of capacity region, which is a set of all simultaneous rates that can be achieved at the receiver from both users. And this region is characterized exactly. The reverse is the broadcast channel. Here we have a single transmitter and two receiver. Single transmitter wants to send information to both receiver. The broadcast channel capacity in the Gaussian case is a special case of a degraded broadcast channel solved by conjecture by Cover, solved by Berkman in the early 70s again. The general broadcast channel is still open, but the Gaussian case is known. Not only the degraded Gaussian case is known, recently even the non-degraded MIMO Gaussian case is solved. I'll talk a bit more about that result later on. Okay, so seems that we're going strong here. Only in a span of a few years in the 70s, we have solved the two important generalization of the point-to-point case. However, if you want to go further, it turns out that the road is tough. The road is extremely tough. And in fact, there is essentially no other networks for which we know the capacity of. For example, let's look at this very simple multi-user channel. So this is the interference channel. Here, we have two senders, like in the multiple access case. But we have two receivers, unlike the multiple access case. Each of these receivers is only interested in the signal transmitted by its sender, not interested in the other guy's message. However, the question is, what is the optimal trade-off of the rates that can be achieved in this channel? Again, it's a question of capacity region. So you may think, oh, wait a minute, there's the two links here, and why not just each link simultaneously transmit, treating the other guy as noise? Certainly, that's a strategy. However, from an information theory point of view, one needs to know whether that's the optimal strategy. And if not, what is the optimal strategy? In other words, perhaps each sender can prepare the signal, structure the signal in a way to help the other guy cope with his own signal, and thereby trading off its own data rate with the other link's data rate. What is the optimal trade-off there? Open question. For 30 years, almost 30 years, the earliest result, one of the earliest results is, and still the best result, is a result by Hani Kobayashi, which characterizes an achievable region. So by achievable region, essentially I mean regions that are achievable by some strategy, but not known to be optimal, So open problem for almost 30 years. And in fact, in a wireless context, a very important problem, Another simple channel is the single relay channel. Here we have a source, a destination. Source wants to send information to a destination. Overheard, the signal is overheard by a relay. The relay can try to help out the source in helping out sending information to the destination. What is the maximum information rate that the source can send to the destination with the help of the relay? This is a question of capacity of the relay channel. Again, a very nice paper written by Stanford folks, Abbas Al-Gamal and Tom Cover in 1979. A lot of interesting achievable strategy, but the capacity is still unknown. Okay, so I would like to describe some of the recent progress that we'll be making on this problem. The one-word summary of this recent progress is really approximate. So to compute the capacity of these channels and other channels, if you think about other channels, this is essentially the simplest possible case. You can think of an arbitrary network where you have multiple source, multiple destinations, and multiple relays as well. And of course, even these basic cases cannot be solved. Those are still open. So instead of trying to solve things exactly, let's try to settle for a little bit less and try to solve an approximation of the region. So you would think that it's a bit of a cop-out, And however, many other fields have in fact gone this route. If you look at, for example, queuing theory, people have long given up on characterizing exactly the queuing dynamics of a general network and has gone on to useful and fruitful approximation, such as approximating the queuing dynamics by fluid or by heavy traffic. And still a lot of good progress can be made by these approximation. Another field is CS theory. Here, instead of looking at exact optimal algorithms, for which many of them are NP-hard, people now have been focusing on, a lot of research have been focusing on finding good approximation algorithms. So let's follow the lead of these fields. And instead of thinking about characterizing exact capacity, let's try to think about approximation. Now, the interesting thing about information theory, I think, is the very close tie from theory to the engineering of communication system. So in the process of doing approximation, we should be respectful of that connection. And to do that, we should try to make the approximation good in engineering relevant regimes. And this line is really where engineering hits mathematics. So approximation, of course, you can define many, many different notions of approximation. But if you want to make an impact on practice, then the approximation should be good in engineering relevant regimes. So the two regimes that I want to talk about today, one is what I called interference limited regime. Okay? So in the interference limited regime, we are dealing with a situation where the noise at the receiver is small compared to the various signals you receive from the nodes. So this is the regime where signals dominate, noise plays a relatively small role. So in this regime, we can focus on interaction between the signals rather than the stochastic noise. If you think about Shannon's point-to-point theory, the whole story is about how to deal with noise, how to make reliable communication out of unreliable random links. Okay? If you move to networks, then we have, in some sense, two fronts to deal with. One, the noise, which was already there in the point-to-point case. But two, the interaction between the signals from different nodes. So we're simultaneously fighting two battles. Interference limited regime essentially says, let's first focus on the interaction between signals, which is really the new part that comes from the multi-user aspect of the problem, and then see how we can go from there. Okay, so this is the interference limited regime. The second regime is the large network regime. So here we're dealing with networks where the number of nodes is large. And here, the focus is on allowing us to develop macroscopic scaling laws to try to figure out how the capacity of network scale with the number of nodes as they get large. So here again is an asymptotic regime, useful for providing some architectural insights to how to design systems for large networks. So these two regimes are essentially the focus of my lectures today. So first, in the morning, the lecture 1 and 2 will be focused on primarily the interference limited regime. Here, I break up the material into two parts. The first lecture will be focused on interference channels, primarily focusing on the two-user interference channel, but I will talk about extensions of that somewhat. So the main result I want to talk about is a characterization of that two-user interference channel capacity to within 1 bit per second per hertz. Okay? This result is sort of the starting point of this research on the interference limited regime. So I want to, in most talks I give at conferences and other meetings, I usually keep it pretty high level. But today, since this is a short course, I would like to focus on how we actually come about getting this result. what was the thinking behind this result? Let me see if I can try to do that. Because I was thinking of this as like a kind of my vision of this short course is like a small seminar type. But now I see that this is like 5 times the size of my normal classes. So you guys were able to get quite a lot of people here. That's good. OK. So that's the basic result I want to talk about.
You got the people here. So
we got the people here.
Speakers.
OK. All right. You're putting pressure on me now. I'm stressed. No, Muriel got the people here. I'm just a tag on. I'm just a tag on here. So now I relieve my pressure.
Muriel, you, and Toby.
OK. So I don't want to stand so close to Gerhard now. I want to stand this side. Pressure is too high here. So I'll give the result, explain how we got it, and then I'll revisit this result through a deterministic channel model. So it turns out that the basic sort of structure of this result can be explained very clearly using a model which is a deterministic model which approximates that Gaussian model. So I want to talk about that. And then I'll use this insight to try to do some generalization to some many-user interference channel, beyond 2 user. So this is focusing on interference. Lecture 2 will be focused on relay networks. Okay. So again, we were able to develop a result which characterizes that relay channel capacity to within 1 bits per second per hertz. I will develop a general result which we're able to solve for the single source, single destination relay network with arbitrary number of relay nodes, normally 1, to within a constant gap, just like the 1 bits per second, but a different number, independent of the channel parameters. OK. So this is lecture 1 and 2. This is this morning. This afternoon, I will talk about large networks. And here, the focus is on networks with many source-destination pairs and many relay nodes. And I will develop some results on information theoretic optimal scaling laws and architectures. OK. So any question? All right. OK. So lecture 1 is on interference channels. So interference. OK. So interference is really a very central problem in wireless system design. If you think about a lot of wireless communication systems, the performance is primarily limited by interference. So how to manage it properly is really sort of at the heart of designing wireless networks. Okay? And you see this phenomenon all the time. For example, if you turn on your laptop, you typically see 10, 20 access points, Wi-Fi access points. And these access points are all interfering with each other. And it is only through some appropriate or some interference management techniques that you can get some decent performance. Okay. In a cellular system, of course, there's also interference between adjacent cells, so-called intercell interference. Systems like CDMA are primarily limited by interference from adjacent cells. So very central problem of wireless technology. Really, there are 2 basic approaches, essentially, or a slight variation of this basic approach. One is orthogonalized transmissions into different bands. Okay. You have multiple interfering systems, and they are orthogonalized into different bands. First approach. Second approach, fully sharing the spectrum by treating the interference of the other users as noise, as essentially Gaussian noise. Okay, so these are the 2 basic approaches, and both wireless systems can be divided into one of the 2 approaches. Very interesting thing about this is that although interference is so central to wireless, no one really knows what is the optimal thing to do. These 2 seems like a reasonable solution, but no one really knows what's the optimal thing to do. And as we know from history of wireless communication and information theory, when we know how to do something optimally, sometimes you get good results. You get a good technology transfer from the theory to the practice. So we should ask this question. And the simplest possible model, I already mentioned a little bit, of capturing this interference problem is the two-user Gaussian interference channel. Okay? I said a few words about it already, but let me now be more careful. Okay, so here we have transmitter 1, transmitter 2, receiver 1, receiver 2. Transmitter 1 wants to send a message to receiver 1, M1. So transmitter 1 sends M1, receiver 1 wants M1. Similarly, transmitter 2 sends M2, receiver 2 wants M2. Now, they will be happy by themselves. However, nature's cruel, and the signals that transmitter 1 send out leak over to the other receiver, just by the nature of electromagnetics. Waves propagate anywhere. And so there's a cross link here, and that cross link has gain H12 and H21. So the four numbers, H12, H21, H22, H211, together with the power of the transmitters and the noise of the receivers characterizes the performance characterizes this channel. So, however, you can, by some parameterized reduction, you can reduce all these parameters into basically four parameters. Okay? The four parameters are basically the signal-to-noise ratio at receiver 1 and receiver 2, and the interference-to-noise ratio at the receiver. I will be using these parameters quite a lot, so let me explain a bit carefully what they are. So signal-to-noise ratio is familiar. It should be familiar to most of us. This is the amount of signal power at the receiver divided by the background noise at the receiver. This is SNR1. Similarly, at receiver 2, you have SNR2. So this is the amount of signal of interest. Interference to noise ratio is the amount of interference that is received from the other link at the receiver divided by the noise. Okay, so this is the amount of interference power divided by the noise. Okay. All right, so we have four numbers here. And let's see what happens. Let's see what results you have. Okay, good. So Gerhard is serving as the...
In the work I do, I usually work with signal to interference plus noise ratio. So why am I not seeing that?
Okay, first, you can certainly compute signal to interference plus noise ratio from this number. So, okay, good. So signal to interference noise ratio, okay, is actually equal to the signal to noise ratio divided by 1 plus the interference noise ratio. Okay, so this is the formula. This is power over noise. This is normalized to be 1, noise to be 1, and this is interference over noise. If you multiply noise throughout, then it's just received power divided by the noise plus the interference. Okay, so now the converse question is, which is, certainly from these two numbers you can compute this number, but no one ever bothered with looking at these two numbers separately. They always just look at this number. And if you treat interference as noise, then essentially the interference goes downstairs, and the performance of your link is only a function of this number. Therefore, if you treat interference as noise, you never need to worry about these two numbers separately. However, here we are interested in the fundamental limits. So we are characterizing the performance in terms of the basic parameters, and we should not assume a priori that you treat interference as noise. It should emerge, if it is true that it's optimal, it should emerge as a result. So that's why we focus on these four numbers at first. Okay, good. All right, so Gerhard is taking the lead here. So follow his lead, yes, good. All right. Okay, just to put this channel into context, okay, results that you may be familiar with. So first, again, as I said, if the receivers can cooperate, okay, if the receivers can cooperate and jointly decode these two messages, then this is just a multiple access channel. This is a channel where you have two users simultaneously sending information to a common receiver. The only feature is that this receiver has two antennas, that's all. Okay, so this is a special case of a multiple access channel, and as I said, the basic result is already known in the early 70s. On the reverse side, if the transmitters can work together, in other words, they can take the two messages and jointly prepared a transmit signal here, then this is a broadcast channel, because you have a single sender now sending messages to two independent receivers. It's a broadcast channel, and in fact, it's a MIMO broadcast channel. And this capacity is recently found a few years ago in a beautiful paper by Gaussian and others in 2004. And in fact, this won the Best Paper Award in 2005. Okay. All right. So the point here is being that the difficulty of this problem is really the fact that neither the senders nor the receivers can cooperate. So in some sense, the interference channel is kind of the simplest model where distributedness is the central aspect of the problem. The fact that each receiver only sees part of what's going on and has to make decisions based on that observation. Okay? So that's why it's difficult. Surprisingly, two-user interference channel, the capacity region is essentially open for 30 years. No one knows what the capacity region is. So let me be more specific and say a few words of the state of the art in 2006. So there is a very special case for which the capacity is known, the capacity region is known. It turns out that if the interference to noise ratio is greater than the signal to noise ratio, in other words, the signal, the cross gain, okay, from a sender is stronger than the direct gain. So it's a signal from a transmitter is heard more loudly by the other receiver than your own receiver. If that's the case for both senders, then the capacity region is known. Okay? And this is so-called the strong interference problem, strong interference channel. And this result is simultaneously solved by Hein Kobayashi in 1981 and Sato in 1981. Okay. For any other parameter range, this capacity is unknown. Okay. The best known achievable region is due to Hein Kobayashi, as I mentioned. The problem of Hein Kobayashi paper, okay, actually, I think one reason why this interference channel problem is so difficult is because of this paper. So if anyone has tried to look at this problem, the first reference that your advisor will tell you is, look at Hein Kobayashi. I also told my students many years ago, look at Hein Kobayashi. That's the best known achievable region. And then they come back after a few weeks, I don't want to do any information theory anymore. I'm not kidding. In fact, one of my students exactly did that. He went off and do something else. And then I said, let's be careful about giving this problem to students. I don't want to lose all my students. So if you look at this paper, these fellows are clearly very smart. But you look at the result, it's really complicated result. In fact, if you try to apply this result to the Gaussian case, it's not really computable. No one knows how to compute it. Okay? And I'll say a few words about this computation question later on when I give more details. So basically, it becomes like a stumbling block of the field, because everybody wants to work on this problem. They read this paper, they get discouraged, and then they go home. And so that's a bit of a problem. And if you look at the result, it really gives very little engineering insight, because not only we don't know if it's optimal, we don't even know how far it is from capacity. We don't even know under what condition on the channel parameters is this scheme any good. So no insight at all. A little bit disappointing. Okay? Now, at that point, there are some outer bounds which exist. But it's unclear how tight they are. So this is the state of the art in 206. I've looked at this problem since my first student, 1998, I believe, 1999. So my students come and go. And after a few students, finally, one student survived and graduated. To explain that result, let me first review the strong interference capacity result. So here, we have the situation where the interference to noise ratio from transmitter 1 to receiver 2 is greater than the signal to noise ratio at receiver 1, and similarly for the other sender. Okay. Okay. So actually, to prove the capacity of this problem, it only takes 5 minutes. Really 5 minutes. And here's the argument. Okay. The idea is that if you think about any achievable scheme that you can come up with, each user has to be able to decode the other user's message. Now, why is that? If you look at, for example, this receiver, because it's an achievable scheme, that means it can decode its own message. Yes? If it can decode its own message, then it can subtract its own message off, cancel its own signal. And what does he have? He now has a clear view of the other guy's signal. But the interference to noise ratio, 2 to 1, is stronger than the signal to noise ratio of its own link, of transmitter 2's own link. And since receiver 2 by definition can decode transmitter 2's message, this guy's in an even better position, stronger link and no interference. And therefore, receiver 1 can also decode transmitter 2's message. So therefore, automatically, if you have an achievable scheme where your only goal is to transmit your own message, automatically you have to be able to decode the other guy's message. And therefore, the information sent from each transmitter must be common information. By common information, I mean information that is automatically decodable by everybody, by both receivers. And so what's happening here is essentially that the interference channel capacity region is basically the intersection of 2 max regions, one at each receiver. Why? Because the 2 messages here are simultaneously decodable at both receivers. And therefore, these 2 messages must lie in the multiple access region at this receiver with the 2 senders, so-called MAC, multiple access. And therefore, the capacity region is just the intersection of these 2. So that's it. So you get a result in 5 minutes. In the next 30 years, is the rest of the story. Yes?
Does anyone build systems like this?
Does anyone build systems like this?
Like in wireless transmission?
As I said, in wireless system, so the most prevalent wireless systems where people put most of the effort is cellular systems. Yes, cellular system. In a cellular system, this is not a very common situation. So this is a problem of common information, but it's not a very common situation. Okay, and the reason is the following: because here we're assuming essentially the cross link is stronger than the direct link. In a cellular system, there's already a handoff. Typically, you do a handoff where you hand off to the receiver which is strongest. So therefore, this is not a very typical situation. And in engineering, people usually try to first solve the typical situation before they get on to the atypical situation. So I would say, no, I don't think so. However, if you look at the evolution of wireless systems, people are now thinking of more ad hoc configuration, where it's not purely just handoff, maybe due to interference between many different types of links and so forth, and in which case this situation may arise, and people are now start thinking about implementing some of this, as far as I know. Yes?
Can this model be extended to the end user? Is there a definition of strong end user interference?
Okay, so that's a good question. It's a bit beyond the scope of this talk, but let me return to that at the end, because I will talk about the many user interference channel. So this argument, okay, I can talk offline, but this argument turns out to be very fragile. If you look at the K user interference channel, it turns out that, so if you think about it, this argument works for a wide range of parameters, right? It's a continuum range of parameters. But turns out that you extend this, try and extend this to K user, there are channels for which you can make this argument, but that's a set of measure 0, if I remember correctly. Yeah. Okay. All right. Good. All right. So good. 5 minutes. We solved half of the parameter range. Now we have the other half to worry about. The other half is when at least one of these two conditions are not satisfied. So this is typically called a weak or semi-weak interference channel. Okay. So this is the open problem for 30 years. And Hein Kobayashi had a natural achievable scheme, essentially related to this idea of common information. So in this case, where the interference is weak, then to make the common information, to make your signal decodable at the other receiver may be too much. In other words, you may be lowering your rate too much to have the other guy decode your message as well. So a natural extension of this idea is to have, instead of purely common message, you can have two messages superimposed on each other, one called common, W, one called private, for each of the transmitter. And the receiver, okay, decode, each receiver decode the two common messages, one from its own sender and one from its own receiver, as well as decoding the private message of its own sender. So in other words, the private message and the common message and the other guy's common is decodable at this receiver, and similarly, symmetrically for this receiver. So common is decodable by all. Private is only decodable by one link. Okay? So this is a natural scheme given the situation here. As I said, computing this region is notorious for the Gaussian problem particularly. First thing is that these are auxiliary random variables. As far as I know, computing these auxiliary random variables optimally, no one knows what they are. No one knows what they are for the Gaussian problem. Of course, you can say, you know what, it's a Gaussian problem, let's use Gaussian auxiliary random variable. Now that's a cop-out, because there's no theorem. There's no theorem saying that. However, you can do it. And then even that computation is very difficult. The reason is actually that it turns out that not only you have to use one auxiliary variable, in general, to get the Hein-Kobayashi region, you have to time share over many choices of this auxiliary variable. So you may need to time share. Now, Gerhard may remember, but I forgot. There's a number, there's a cardinality bound here on how many to time share. Anyone remembers?
Someone here knows. There's a couple of students who worked on that problem here, or who have colleagues who worked on it, and they know better than I do.
Is it 9 or 11 or 7? I remember one of those numbers.
Well, there's something like 4 in terms of time sharing. There's 4 modes, I think, or 5. There was a paper with 5. There was a paper that showed it was 4 was enough. Someone here knows, I think.
Some participation would be good, yes. Yes, I see Gerhard trying very hard here. Really? Okay. Because I thought in its original paper, it was 7 or 9. It was reduced. Okay, very good. Still, 4 and 5 is quite a bit here, considering that even if it's 1, we cannot compute the random variable. So it's a tough job. So as far as I know, no one has been able to compute this Hein-Kobayashi region. Okay. So at that point, this is after a few students I lost, I said, this is no good. And then I have this one student, very good student. His name is Raul Aiken. He's about to graduate. And I think now I learned a new research strategy, which is the best time to get a productive student, to get productive results from a student, is 6 months before he graduates. Because he has a job waiting for him already. He got to go and earn some real money. and yet I have the authority to sign. So I said, Raul, you've been working on interference. Actually, we were supported by an NSF grant at that time on the problem of spectrum sharing. And to me, interference is kind of central to this problem of spectrum sharing. I said, Raul, you got to say something about this two-user interference channel before you go off to HP. And at that time also, I have a grant student, promote student, Hua Wang, who actually spent the summer with us. And we were working hard. So we spent that summer working every day on this problem. And we said, geez, this is a really tough problem. Even computing it is so tough. So why don't we think about approximation, okay? And as I said, approximation should be guided by regimes that are interesting from a practical point of view. So let's look at a regime that's interesting. So essentially in communication, there are essentially two regimes that one can look at. First regime is the low signal-noise ratio regime. At low signal-noise ratio, that means the noise is large compared to the signals. Okay? However, if you think about the problem is the interference channel problem. Interference channel, when the noise is limiting, is not very interesting. Because interference channel, you want to focus on what to do with the interference. So low SNR is a bit not very interesting. Yes?
So you said that Han and Kobayashi have the best suitable region, right?
Yes.
But if it is not computable, how do you know it's the best?
Because no one, okay, that's a good question. Maybe I should say it's the only achievable region that. Well, look, I did not make a mistake. If it's the only achievable region, it's also the best achievable region, yes? Very good question. Very good. Yeah, I never thought about it. I mentioned this like 10 times, but never thought about it. Everybody says the same thing, right? So, all right. So we said, okay, if we want to find a regime of interest, I think it should be the high signal noise ratio and high interference noise ratio regime. So in this regime, the noise is playing a relatively small role. The interference becomes the focus. The interference becomes the focus. And so we think, okay, how do we make progress? Maybe we could try to do something here in this regime, and then Raul can graduate. Now, if you think about performance in this high SNR regime, from point-to-point communication, we know that there's a very important parameter that one can calculate. It's called degree of freedom, and that is a very important parameter. And if you, I'm sure a lot of you have exposure to MIMO, degrees of freedom is kind of a very important parameter measured there. And so we start thinking along these lines. Okay. All right. So we start by calculating the degrees of freedom for the achievable schemes that we know of, and we call them baselines. Okay. So to simplify my notation, let us focus on the symmetric case. So in the symmetric case, I'm assuming that SNR1 is equal to SNR2, and INR1 is equal to INR 2 to 1. Okay? So I'm assuming the direct links have the same gain, and the cross links have the same gain, but not necessarily equal to each other, of course. So this is a symmetrical channel, just to keep the notation simple. So again, back to the baseline. One baseline is the point-to-point capacity. This is the capacity that you get by when there's no interference. And the degrees of freedom there, the degree of freedom there is defined to be the capacity normalized by log of SNR as SNR goes to infinity. And this calculation can be done for this capacity. It's equal to 1. So this is a so-called pre-log. Okay? This is the parameter before log of SNR. It tells you that essentially you have 1 dimension per second per hertz to communicate. So this is a well-known parameter, no controversy there. Now, let's look at an achievable rate for the orthogonalization scheme on the interference channel. So if we orthogonalize, that means we give half the band to each user. So you have half the rate, but you have twice the power. So you have half log plus 2 times SNR. So on you don't have twice the power. So you have the same power, but because you have half the degree of freedom, your power per degree of freedom, SNR, is doubled. So this is achievable rate per user by orthogonalization, our first baseline. The degree of freedom there is obviously half. You can do this calculation, and it's just a pre-log, so it's half. Okay, then we say let's calculate the third scheme, the second scheme I should say, which is treating interference as noise. As I already write down, the rate is given by log of 1 plus the signal to interference plus noise ratio. So treating interference as noise, you get the signal to interference noise ratio. So in other words, you are treating the interference as Gaussian noise. You're using Gaussian codebooks, and you're treating interference Gaussian noise. And you get this rate. Okay? So we ask the question, well, how many degrees of freedom do we get from this rate? Okay? So, all right, so we do the computation. So let's do that. I'm really glad that there's some real blackboard here as opposed to those smelly whiteboard. Okay, so let's compute. Right? So this would be the limit that I'm computing. Okay? Now, there's a problem here. I don't know how to compute this limit. Why? Because INR is an independent parameter from SNR. So I don't know how to compute this limit. So there's not a very natural generalization from that. Okay, so if you think about the situation, we have the following situation. So let's go back to the parameters that perhaps you're more familiar with. Okay. Can people see it here? Yeah, okay. Okay, so here the problem is that if you want to compute the degrees of freedom, you're actually worrying about taking limits of this system, as something goes to infinity, presumably as the SNR goes to infinity, but there are many ways of taking this limit. And here's one way. I look at all these gains, and I assume each of the transmitter has the power P, okay? And this you can always do by absorbing any difference in power in the gains, okay? And then, instead of taking SNR to infinity, you take the power to infinity, okay? Which certainly implies the SNR going to infinity. And now, when you take the power to infinity, you take these parameters, 4 numbers, to be fixed, okay? So this seems to be a natural extension of the degree of freedom. But let's see from a practical point of view where this would take us. Okay? So can anyone tell me? So this is a class, right? Not a seminar, so there's a class. So a class means participation. Participation means, can you compute this limit for me? All right. Good. What is this limit? Okay, so let's see. All right. So SNR is equal to P times H 1, 1 square, yeah? I'm normalizing noise to be unit variance here, okay? That's enough. The interference to noise ratio is P times H21 square, okay? So I'm assuming symmetry, so H11 equals H22 and H21 equals H12, okay? So if I plug that in, okay, all right, okay. So what is this limit? This is 0, right? Because P is going to infinity, okay, let me make sure this is correct first. P is going to infinity, so this whole thing is going to be something like log P minus log 1 plus this. This would become log P2, so log P will cancel, and this is the large term. So this is now a constant divided by downstairs, which is going to infinity, so this goes to 0. So therefore, now you may say that, hey, there's a problem with this limit. So when a limit comes out to be nice, to be 0, then you cannot say, oh, 0 means let's go home. Now, the problem with 0 is that obviously, if you want to use this limit to say something about a finite SNR, finite NR system, it's not a very useful statement. Because the actual performance is, of course, not 0. It's only that this limit is 0. Okay? So therefore, this limit is not very good. It's hiding too much information. Because my philosophy about taking limits is that the limiting system should say something about the finite parameter system. This limit is too crude. It's destroying everything. So that was our first starting point, which was, how can I take a limit such that still I'm looking at the highest NR regime, okay, but I can retain some of the structure. Okay, so let's see how that works. Now let me rewrite that expression. So if I rewrite this expression, I can assume, since highest NR, I can take away this 1, and I can take away this 1. So this can be approximated by log of SNR minus log INR. Okay? So essentially what happens in this limit is that both of them are going to infinity, but at the limit for large P, the two numbers are very similar, and so you get washed away. So a natural way of taking limit to reflect the penalty due to the interference, which is the minus term, is to take a limit in such a way to keep the ratio of these two numbers fixed. Okay? So that the penalty is reflected in the limiting system. So that was our starting point, is to find a right way of taking a limit so that the degree of freedom is saying something meaningful about the finite system. So that's how we define degree of freedom. So I argue that degree of freedom is actually not a uniquely specified parameter in a multi-user network, unlike the single point-to-point network. So we're free to define our own degree of freedom, and that's how we define it. Okay, so we let both SNR and INR to grow, but we fix the ratio of log INR and log SNR to be alpha. So in other words, we're fixing the ratio of these two numbers. And so using the strategy of treating inference noise, we can now calculate the degree of freedom. Yes?
Right over here.
Oh, okay. Yes.
How did you get rid of one over here? 1 plus
1?
Yes.
So here what we're assuming here is that you're in the regime where you have high data rate. Okay? So high data rate means that these two, the ratio of this number should be large. And so that's why I can ignore the 1. Okay? So I'm studying the regime where the data rate is high, but both the signal noise ratio and inference noise ratio is high compared to the noise 1. Sorry? This one or this one? I was explaining this one. Yeah, so I'm assuming that this ratio is large. Right? So I'm assuming that I'm in a regime where the data rate is high. So for example, SNR could be 20 dB, and INR could be 10 dB. So the ratio is still about 10 dB, and so 1 it can be ignored.
So it's not the case here. Like in the first case, when you have when you are linking P to infinity.
Yes.
So it doesn't happen.
When P goes to infinity, what happens here is that this ratio is bounded. This ratio is bounded by the ratio of the gains.
It's not necessarily goes to infinity.
Sorry?
I mean, it's not going to infinity, so you can't ignore that one. Like when you're considering this multiplying by H11.
Right. But in any case, it doesn't matter, because whether there's 1 or no 1 here, this limit will still go to 0. Yeah. Okay. But if you take limit this way, you can see that the degrees of freedom is now a function of alpha, where alpha is the ratio of these two numbers. Now, what are these two numbers? They actually have some pretty good meaning, because in communication, we typically measure signal noise ratio and INR and interference noise ratio in the dB scale. So this is nothing but the ratio of these two numbers, these two parameters in the dB scale. Okay. All right. So now we can plot what's going on. Yes?
Don't you have to specify just a little bit more about that limit? I think that's the question, right? If both SNR and INR go to infinity and they both go to infinity, so that SNR over INR happens to be 1, then R is log of 2 divided by log SNR. You don't get 1 minus alpha.
You get 0.
Yeah, so you have to specify how SNR...
No, you still get 0. I think it's still good.
Oh, are they going to 0?
Yeah, if SNR and INR is going like this, then the ratio is 1.
I see.
And this will be 0, so it's still consistent.
I didn't see the logarithms, yes.
Yeah. Okay, good. So it's still consistent. I'm just using this as a motivation, not as a proof. But okay. So now we can do plots. And here's the plot that I'm going to make. So I'm going to plot as a function of the parameter alpha, which is the ratio of the INR and SNR in dB scale, the performance, which is the symmetric capacity or the rate, divided by log SNR. Okay? So you can think of this ratio as the ratio of performance normalized by the capacity of a point-to-point link without interference. So this ratio tells you how much performance hit you get due to interference. When there's no interference, very little interference, the number should be 1, as it is. I'm now plotting this curve 1 minus alpha here, which is treating interference as noise. You can see that as the interference increases, your performance continuously degrades. Okay? And essentially beyond alpha greater than 1, you get hardly any rate. So this is a limiting statement. It doesn't mean you get 0 rate, but in the limit you get 0. Okay? So therefore you get quite poor rate. When you orthogonalize, you get half. You get half the degrees of freedom. And this half is independent of how much INR there is. Why? Because you're already chopping up your resource into 2 halves already. Okay? So we have this situation. Now if you look at this situation, you can see immediately that none of the two schemes are optimal over the entire parameter range. And in fact, when alpha is small, that means the interference is small. Orthogonalizing is not a very good idea, because the interference is so small that you're paying too much a price to reduce the degrees of freedom by half. Treating interference as noise is a better idea. It's a better idea. Okay? On the other hand, when the interference is strong, treating interference as noise is not a very good idea, and orthogonalizing is better. And the cutoff, the intersection, is precisely at this point half. Half means that the INR is half of the SNR in dB scale. So one is 10 dB, one is 20 dB, for example. Okay. So now the next step in our thought process was, well, the natural thing to do now is to try to plot what happens to the Hainen-Kobayashi scheme. Now, as I said, Hainen-Kobayashi is difficult to compute. However, in this limit, it turns out that, number one, we don't need time sharing. Time sharing is not needed. Number two, we still don't know what to do with the non-Gaussian input, but let's stick to the Gaussian input. So we can now calculate an optimal Gaussian Hainen-Kobayashi region in terms of the degree of freedom. And it turns out to have this shape. Okay? Okay, so now we have a third curve. And to do a sanity check that we didn't make any mistake in the calculation, it's good that these two curves, this curve, is above these two lines. Because actually, if you think about it, Hainen-Kobayashi actually already include the strategy. Okay? So good. So this curve demonstrates the following fact. Number one, when alpha is less than 0.5, optimal Hainen-Kobayashi essentially sends no common message. Because this part is essentially treating the interference as noise. That means you're not trying to decode any of the message from the other guy. Okay? So when the interference is weak, treating interference as noise is degree of freedom as good as the optimal Hainen-Kobayashi scheme. Okay. Now when alpha is greater than half, then your interference is strong. Interference is stronger. And now there's some hope of improving performance by making some of your bits to be decodable by the other receiver. And in fact, this curve is alpha, and this is 1 minus alpha over 2. The interesting thing about this is that actually the performance of Hainen-Kobayashi is not monotonic in alpha. So in other words, as you increase alpha interference, the performance sometimes gets better, sometimes gets worse. Okay? It may be surprising at first sight, but we were searching for explanation. But then at the end of the day, we said, why do we need to explain it? That's just what it is. And that's what it is. Okay. Now, after alpha greater than 1, what is this regime? This is a strong interference regime. And in fact, this curve is precisely the curve where you can send common information only. Common information only. So Hainen-Kobayashi now, at this point, sends 0 private information. And after alpha equals to 2, you get a flat curve, 1. Now, just to remind you, between alpha 1 and 2, you do not get back to the full degree of freedom of the point-to-point non-interfering link. Okay? Because you still have to worry about lowering your common information to make sure that everybody can decode it. So you're still perhaps limited by the other users. However, when alpha is large enough, okay, then you can get back to the point-to-point performance. Why? Because when the cross-link is so strong, you can now decode the other guy's message, treating your own message as noise, strip it off, and now you have a clean point-to-point link. Okay, yes?
What do you mean by optimal Hainen-Kobayashi?
Optimal Gaussian Hainen-Kobayashi. So I was very specific here. So what I'm saying is that I'm now using a Gaussian U and a Gaussian W. Remember that U and W, the private and the common. Gaussian auxiliary variable. And I try to optimize over the variances of these two things, subject to the total power constraint. Okay? And I get that curve. Okay? So this is encouraging. Raul was a bit happy because he said, maybe I'm one step closer to getting out of this place. Yes?
Why can't you use the same strategy for alpha is equal to 1.5 that you are using for alpha is equal to 2?
So, okay. So alpha equals to between 1 to 2. Okay, this is the case when the capacity region is the intersection of two max, right? Okay. Now, so the common messages are jointly decodable at each of the receiver. Okay. Now, in general, you cannot say that I want to decode one message before the other message, because they may lie on some point on the sum rate line. But however, when the interference is strong enough, then the operating point turns out to be at a corner point where you decode the other message first, and then you decode all message. In general, you'll be somewhere on the sum rate line, and you still take a performance hit compared to the point-to-point performance. Okay. All right. Maybe it's not a good idea encouraging too many questions, because there seems to be some experts in the field here. All right, good. It's only good to encourage questions when you know that the students don't have very good questions. Okay, very good. All right, so that's the curve. Now, let's look at the scheme itself. All right, and my philosophy about information theory is it's much more fun to look at the achievable strategy. And without a good understanding of achievable strategy, it's very hard to prove good outer bounds. So we're starting with achievable strategy here. So let's look at the structure of the degree of freedom optimal Gaussian high-end Kobayashi. Okay. First, as I mentioned, you can show that you only need a single split. So in other words, you only need to do one split, no time sharing required. 2, which is the key here, the key of the solution here, is that the private power is said to be very special. So it turns out when we did the optimization, the received power of the private turns out to be at the noise level at the other receiver. So it's not some arbitrary power, but it's a very special power. And let's get some intuition as to why this is the right thing to do. Remember, the private power, the private signal, is the part that is not decodable at the other receiver, okay, or not supposed to be decoded by the other receiver. So therefore, when the other receiver decodes, this interference noise ratio, due to the private power, is essentially going to be additional interference, additional Gaussian interference. Okay? So the question is, why do I want to set this to be 0 dB? By 0 dB, I mean it's at the noise level of the receiver. If you look at the performance of the receiver, so what's happening to the receiver? He's trying to decode his own message at a signal-noise ratio, okay? But there's this uncancelable interference due to the private signal from the other guy. So roughly speaking, to a first order, the performance he's getting is roughly of this form. Log 1 plus signal-noise ratio divided by the interference noise ratio, not due to the whole thing, but due to the interference caused by the private power. And let's plot this performance as a function of the I and R. And you'll see what's happening is that there's essentially roughly 2 regimes here. First, when the interference noise ratio is much less than 0 dB, the performance of that link is essentially the interference is actually not visible. Why? Because the interference noise ratio, when it's less than 0 dB, is essentially a noise-limited system. So your performance is essentially driven by the noise. And you don't take much of a hit of the performance here. So it's a pretty flat curve. Okay, so this part of the curve is insensitive to the interference. When the interference becomes larger than 0 dB, your performance takes a drastic hit from the interference. Okay? So therefore, setting the interference noise ratio to be 0 dB actually makes good engineering sense. Because what you're doing is you're trying to figure out a sweet spot where the damage created by the private message to the other link is limited, small. So you want to push it to this point where small, still small, but you can still get a high rate in your own link since SNR is greater than INR. So in other words, you're trying to say that, hey, I don't want to create that much interference to you, but at the same time, I want to push as many bits through as possible in my own link. So this seems like a reasonable solution. And in fact, when we did the computation, that turns out to be the optimal power allocation to get the degree of freedom result. OK. So now at this point, we ask a harder question. We limit ourselves to Gaussian Hana-Kobayashi. OK. Now, the question is, can we do better? Perhaps by using non-Gaussian input, we could do better. We could do better. Or maybe we can even use another scheme, completely different from Hana-Kobayashi. And perhaps we can do better. Answer turns out to be no. No in the sense that there is no other scheme you can get this degree of freedom better than the red curve. So in other words, this red curve, W curve, is indeed the optimal degree of freedom, period. Gaussian or not Gaussian, Hana-Kobayashi or not Hana-Kobayashi. And to prove this result, we need an upper bound. Okay? Okay, so now, at this point, we have a candidate achievable scheme. Okay? And now we need to prove an upper bound. And to prove an upper bound, we look at the literature. And a very common bound that people use for the interference channel in the literature is the so-called Zee channel, or the one-sided interference channel bound. So the idea here is simple. You remove one of the link, or equivalently, you give the message of this guy to this receiver so that he can cancel that off. Okay? So this is a sign information bound. It's called a Zee channel bound because when you remove this link, it becomes a Zee channel. And you are essentially giving X1 to receiver 2 as sign information. Okay. Now, yes?
The Zee interference channel, right? Not the Zee channel where you have separate.
Sorry?
This is not the Zee channel where each user, each transmitter could have a separate message for each receiver.
No. All along, I'm just focusing on the most basic model where each transmitter has one message to its own receiver, and this is the Zee interference channel. Yeah. Actually, I don't really like the word Zee too much because sometimes I write this way, sometimes I write that way. It's just one-sided interference channel, But okay. So how good is this bound? All right. So now that we have this degree of freedom framework, we can actually calculate this bound, okay, in the limit of this degree of freedom. And it turns out that when you calculate this bound, you get a nice curve, and you get this green curve. And it turns out to match exactly the capacity curve, or the Hana-Kobayashi curve, the optimal Gaussian Hana-Kobayashi curve, at exactly this point, between 2/3 and 1. So this is a 2/3, and between 2/3 and 1. Less than 2/3, the Zee channel bound is loose. Okay? So we ask ourselves, what's happening here? So basically, if you think about our scheme, our achievable scheme, there are actually two distinct regimes of operation. Okay? First, when the interference to noise ratio and the alpha parameter is greater than 2/3. So this is the case when interference is strong. Okay? You can look at the two common message, and remember that the receiver has to decode the two common message. Okay? In this scheme, treating the private message as interference. So you can draw out two MAC. One corresponds to each receiver. So these are the two MACs. One corresponds to each of the receiver. And if you look at the intersection, that's a set of achievable rate. And the rate that we want to achieve is symmetric, so it's this point in the middle. So this rate is smack in the middle or on the 45-degree line. Okay, so now let's imagine what happens when we do the Zee channel bound, and why the Zee channel bound has any hope of actually is good here. when we take out x1, that means we are decoding one of the common message for free. Yes? So that means we are removing one of these constraints. Which one? We're removing this constraint. Because this is decoding both of the common message. Okay? And you are giving the message x1 for free at the receiver too. So what you're doing, okay, is you are potentially removing this constraint, relaxing it. Now this constraint, if you look removing it, this rate doesn't necessarily go up. Because this constraint is biting by two set of constraints at both receiver. So when you remove one of them, the other one can still be active. So that's why there's some hope that the Z channel bound is good. And in fact, calculation shows that in fact the Z channel bound is good. Okay? Now you look at the other regime. Okay? In the other regime, it turns out that the MAC intersect like this. So in other words, the performance limitation is not due to the sum rate constraint, but it's due to the marginal rate constraint. Marginal rate constraints. So now, let's think about what's the problem when you remove one of these constraints. When you remove one of these constraints, this point immediately go up. So therefore, there's no hope that the Z channel bound will be tight for our scheme. And in fact, if it's not tight for our scheme, then there's no hope that our scheme will be optimal. So therefore, the Z channel bound is definitely not going to match the achievable strategy that we have. Okay? So that's the problem. So that's the problem. And in fact, this alpha parameter turns out to be delineating these two situations at a threshold of 2/3. Okay? So now, we have to devise a new upper bound. Okay? Now, so what new upper bound to use?